Good morning. I'm spot on weather meteorologist Matthew Euler. And today we're going to take a look at another training session. And I really thought this would be appropriate. Now that we're in the month of October, we're going to start getting in progressively later and later into the fall and into the winter. And we're going to see more and more frequency of these low pressure systems, these mid-latitude cyclones, as well as the anticyclones moving across the United States. This is an image of a very tightly wound and wrapped up extratropical low pressure system. Comma cloud is definitely visible here on the satellite image with a frontal boundary extending southwestward along and outside of the low pressure system. And this particular image has happened in wintertime right off the east coast of the United States. A lot of cold continental polar air is pouring off the eastern U.S. in over the warmer waters of the western North Atlantic. So we have some very dynamic systems to talk about today in the training with mid-latitude systems, and I'm going to divide this up into multiple parts. This will be part one of mid-latitude systems. First thing we want to start off with today on the training is what's known as system strength terminology. Okay. We really need to get a general introduction to intensity of these mid-latitude pressure systems. And what is circulation intensity? Simply put, it is a measure of the strength of wind flow around a system. With lows, the stronger the cyclonic flow, the more intense that low pressure is. And a couple terms we use in conjunction with low pressure systems, we use what's known as cyclogenesis and cyclolysis. Now, cyclogenesis is just simply the development of cyclonic circulation or an intensification of an existing cyclonic circulation, while cyclolysis sounds a lot like a villain in a Marvel movie. Cyclolysis, however, is disappearance or weakening of cyclonic circulation. When low pressure systems weaken, we say they're undergoing cyclolysis. When we have low pressure systems that are just developing, perhaps intensifying, you'll hear a meteorologist, they'll use the word cyclogenesis. Now, cyclogenesis and cyclolysis refer to the number of isobars. Now, isobars from past training, iso literally means equal, and bars means lines. Equal lines of barometric pressure, isobars. And they encircle each of these pressure systems, whether it be a low or a high pressure system, not the central pressure of the system, but they encircle the low itself. They encircle that system. So cyclogenesis and cyclolysis refer to the number of isobars encircling the system. The more isobars you have over a more tightly packed, shorter distance, it's going to mainly be a cyclogenesis situation. The further those isobars spread apart, that indicates weakening of the thermal temperature gradient as well as the wind field around these pressure systems, and that's going to result in what's known as cyclolysis. So here's an example with low pressure systems. Generally what we have going on, we're giving you an example of both cyclogenesis and cyclolysis. The image on the left shows an area of low pressure with its cyclonic circulation around it as depicted by the wind barbs. And the winds right at this point are 15 knots. And this is as of 00Z on Monday. If I move 12 hours later to the middle diagram, my overall number of isobars has increased. So you notice in one image on the left, those dark solid lines around these pressure systems are known as isobars, or lines of equal barometric pressure. And you'll notice on the image on the left, I only have three isobars surrounding that low pressure system. The image in the middle with the purple shading, that's 12 hours later, and I now have 4 isobars encircling my low pressure system. And the winds have also picked up in strength due to the tightening pressure gradient, due to the greater pressure difference over a specific distance. And my winds are picking up now to 25 knots. But you notice how my isobars, they increase in number. You notice how my wind speeds are getting stronger. And this is an indication of deepening low pressure and a case of cyclogenesis. If I go 12 hours later from that to the image on the right, now I'm moving to 12 Zulu time on Monday, and now my winds have decreased down to 5 knots. and my isobars have got further apart. They're further more widely spaced apart, and there's only 2 isobars now on the image on the right. So you'll notice how we went from initial development of a low, far left, strengthening low pressure, deepening low pressure in the middle with cyclogenesis, and then for the image on the right, cyclolysis, as we have weakening winds as well as a weakening pressure gradient or a number of isobars around the low itself. With high pressure systems, the stronger the anticyclonic flow. Now when I say anticyclonic, all I'm referring to is a clockwise flow of air around the center of the high pressure system. The stronger the anticyclonic flow, in other words, the stronger the wind flow around the high, the more intense the high pressure is. Now there's 2 terms we use associated with high pressure systems, and these are known as anticyclogenesis and anticyclolysis. And with anticyclogenesis, this is the development of anticyclonic circulation or the intensification of existing circulation. And with anticyclolysis, it's the weakening or disappearance of anticyclonic circulation. Now, both anticyclogenesis and anticyclolysis refer to the number of isobars encircling the system, not the central pressure itself. So again, we're utilizing those solid dark lines, those lines of equibarometric pressure, the isobars, in determining whether we have anticyclogenesis or anticyclolysis. Let's take a look. Just like we did with low pressure systems, this is a high pressure system now, and we're showing the time frames at the very top, horizontally across the top. We're starting off with the image on the left. So we have this high pressure system, we have a clockwise anticyclonic flow of winds around the high, just like the hands of the clock on your wall. The winds are flowing from the north on the front side of the high, from the south on the back side of the high. In general, we have 3 isobars surrounding the high pressure system there on the image on the left. Okay, the winds are about 15 knots on the front side of the high, as well as on the south side of the high. 12 hours later, let's move to the middle image, and you notice those solid dark lines, how I get more wrapping around that high pressure center now? I now have went from 3 isobars on the left to the middle image. I now have 1, 2, 3, 4 isobars now, lines of equibarometric pressure, surrounding my high in the middle there with the purple shading. 12 hours later, 25 knot winds now wrapping around the high pressure system. This is a case of anticyclogenesis, where we are increasing the number of isobars, we're packing them in rather tightly, indicating that we have stronger wind flow. And then if I go to the image on the right, this is a case of anticyclolysis, where my wind speeds are now decreasing because my pressure gradient, the lines of equibarometric pressure, those isobars, I only have 2 of them now, the far image on the right, encircling that high pressure system. Therefore, it's undergoing a weakening state. The high pressure is weakening in a case of anticyclolysis. Now, a real case of anticyclolysis would be in the wintertime, where you typically have this very strong, cold Arctic high pressure system associated with very cold continental Arctic air. And as that high pressure system comes down out of Canada and moves into the northern plains, to the Midwest, it's still fairly strong. Still a lot of wind motion associated, a lot of wind energy associated with the high pressure system. Behind typically very strong cold Arctic fronts, these strong highs come down from Canada. And as it continues to move further to the southeast, let's say that high pressure system is moving from the Midwest to Georgia to the southeast. As it continues to transit southeast, that colder Arctic air is eventually going to become modified, moving over a warmer surface, which is going to result in ultimately an anticyclolysis situation where the high pressure system eventually will weaken. All right, so with system strength terminology, we also have to talk about central pressure as well as central height. Now height, I refer to height when I talk about upper level charts. 850 millibars, 700 millibars, 500 millibars, 300 millibars. 850 millibars is about 5,000 feet as a reference for you. 700 millibars, standard level, is 10,000 feet. 500 millibars, 18,000 feet above the ground. And then 300 millibars is way, way high up there, 30,000 feet where the jet stream typically resides. When I talk about height, I'm talking about those upper level charts. When I talk about pressure, I'm talking about surface charts right here on the Earth's surface with surface highs and surface lows. So in general, with lows, the lower the central pressure or the lower the upper level height, the stronger the system is. And there's two terms we use when we talk about surface lows in particular. We talk about deepening and filling. And with deepening, this is a drop or a decrease in central pressure or height. With filling, this is an increase in central pressure or height. So a low pressure system is either going to undergo deepening, where the central pressure is dropping, or it's going to undergo filling, which is rising barometric pressure at the center. So again, just like we did with the cyclogenesis, cyclolysis, we're now going to talk about with surface lows. We'll show you some examples of deepening and filling. The image on the left, I'm starting off at about 00 Zulu on Monday, and I have area of low pressure, and the central pressure is at 1002 millibars. You see the 1002 underneath that low pressure system. I have two isobars surrounding my low pressure. If I move 12 hours later to the middle image, notice my central pressure has dropped from 1002 millibars on the left down to 990 millibars in the middle. And this is an example of the central pressure decreasing, a process in the atmosphere known as deepening. That's a 12 millibar pressure drop between the image on the left and the middle image. So that's, and you notice the number of isobars also has increased and has really got tighter or more tightly packed around that central pressure, that low pressure system around it. If I go further over to the right, 12 hours later now, notice that my central pressure from the middle graphic to the image on the right, it increases from 990 millibars to 1005 millibars. This is a process in which the central pressure is rising, or an atmospheric process known as filling. Now with surface high pressure systems, the higher the central pressure, the higher the height, the stronger the system is. And we usually use two terms associated with high pressure systems, and these are building or weakening. And when I have a building high pressure system, this is an increase in central pressure or height. On the upper level charts, my upper level heights are building. That means my high pressure system at the surface is ultimately getting stronger. Now weakening is a decrease in the central pressure of a surface high, or the decrease or drop in the height, upper level heights. Here's an example of building and weakening when we talk about high pressure systems. The image on the left shows a 1030, see that 1030 below the H on the image on the left? It's a 1030 millibar high at 00Z on Monday. 12 hours later now, we go to the middle image with the orange shading. Notice how the central pressure is now 1040 millibars. So we went from 1030 to 1040 millibars, an increase of 10 millibars over a 12-hour period. Whenever we have an increase in the central pressure of a high pressure system, that increase is known as building. Process is known as building. And then if you continue moving on to the far right image, you'll notice the high pressure system 12 hours later now at 12Z on Monday is now down to 1025 millibars. So you notice about a 15 millibar pressure drop, central pressure drop of the high. And that's a process in the atmosphere known as weakening. So just showing you some examples of deepening, filling with low pressure systems, building and weakening with high pressure systems. Now when we talk about circulation intensity, central pressure, that usually changes in a similar manner when we talk about intensity and central pressure. In other words, these two are really directly proportional to each other. When one changes in one direction, the other changes as well in that same direction. So circulation intensity and central pressure, they can sometimes change in opposite directions too. So that is a possibility. With, for example, daily heating and cooling, diurnal heating and cooling is the main reason for periods when cyclogenesis, cyclolysis, and deepening and filling do not coincide. So you may have a case to where you have an area of Arctic high pressure again coming down from Canada in the wintertime, and as it continues again to move towards the southeast, the underlying ground is warmer and warmer, and that's going to result in, especially during the daytime if you have sunshine, that's going to result in an opposite case of basically a building that's going to be, instead of anticyclogenesis, it'll be anticyclolysis temporarily. So situations can sometimes dictate where these act in opposite directions. Now, physical processes affecting the development of pressure systems. Petterssen, in 1956, he came up with these ideas. This was a huge breakthrough in the field of meteorology, especially when we talk about synoptic scale meteorology. He found and determined that there's something known as thermal advection, and that is temperature advection. A fancy way to say temperature in meteorology is to say thermal. And this is an asymmetrical occurrence. This advection occurs asymmetrically around baroclinic systems. Now, just to keep this in simple terms, asymmetrical shapes are those that are more elongated. Symmetrical will be more circular or well-rounded. Asymmetrical sometimes are stretched, and they're not a perfect circle at all. So let's first take a look at thermal advection around a baroclinic low. Generally what we see when I have the initials WAA, that means warm air advection. And when you see the initials CAA, that means cold air advection. So warm air advection is a fancy way to say warmer air is moving into your area. When I say cold air advection, it's a fancy way to say that colder air or colder temperatures are moving into your area. So with baroclinic lows, I get this warm air advection, typically out ahead of the baroclinic low on southerly winds. Think about the circulation around low pressure systems in the northern hemisphere, and it's generally counterclockwise. So you get southerly winds on the front side of low pressure systems, and you get northerly winds on the back side to the west of surface lows. And so warm air advection on that front side of the low pressure system is going to cause surface pressure falls and upper height rises. Why do you think that's the case? With warm air advection, generally the atmosphere is bringing in warmer and less dense, warmer and moist air on southerly winds when you have warm air advection in the northern hemisphere. And when you have warm, moist air, it is much lighter than cold, dry air, and as a result, there's less pressure or force exerted on the surface, so you have surface pressure falls with warm, moist air because it's lighter, it's less dense. And then you get the upper height rises also because the atmosphere is going to expand. It's going to expand and get taller, grow taller in vertical depth when you have warmer air moving into an area. Warm air again is less dense, so it wants to rise, and as it rises, it's expanding. Cold air advection, on the other hand, will cause the opposite effects. Surface pressure is going to rise and upper heights are going to fall. And the reason the surface pressures are rising, think about when cold, dry air comes in behind a good, strong cold front in the wintertime. The cold, dry air is going to be much denser. Therefore, it's going to cause the surface pressure to rise. There's more force per unit area with cold, dry air. With upper height falls, think about when the atmosphere is colder, it's going to want to become more compact because the denser, colder air. So the vertical air column is going to shrink or get shorter when you have cold air advection coming in. Now, weak thermal advection does occur at the center of low pressure systems, but it's weak. The main advection, asymmetrical shapes you get around low pressure systems are going to be out ahead of that low pressure system some distance and then behind that low pressure system. With baroclinic highs, with high pressures in the northern hemisphere, we need to think about a clockwise flow of air. So typically on the east side, out ahead of the high, you have northerly winds, and on the west side, behind the high pressure system, you have southerly winds, more of a clockwise flow. And with cold air advection, this is going to cause surface pressure rises and upper height falls. So that stays the same, right? Surface pressure rises and upper height falls are going to be associated with cold air advection. Just they're in different locations in association with a low and a high. And then warm air advection is going to cause those surface pressure falls and upper height rises, just like I explained on the previous slide. And there's weak thermal advection occurring at the center of high pressure systems as well. These systems are what really causes the changeable weather that we experience here in the United States in the fall and the winter time. Even in the early spring, we still have a lot of cold air trying to move south and warm air trying to move north. So you get a lot of cold and warm air advection, fairly intense low pressure systems. The greater the temperature contrast, the greater the amount of energy, and therefore the deeper or stronger the low pressure system will be. Here's an example on a thickness chart showing you what a baroclinic low and a baroclinic high look like, as well as their temperature advection patterns. The image on the left shows a very intense low pressure system over northern Missouri, and there's your frontal boundaries extending. We have a cold front extending south and southwest out of the low pressure system down into Texas. There's a warm front that's running itself across, stretching across northern Illinois, northern Indiana, into northern Ohio. And we got a lot of wind energy. Those dark solid lines are the isobars, or lines of equilibric pressure. We have a steep pressure gradient. We have some fairly strong temperature contrast going on. And you'll notice the hashed area to the north of the warm front. We have warm air advection, the initials WAA. So anywhere north of the warm front across Minnesota, Iowa, Wisconsin, Michigan, we have warmer air, warmer and moister air trying to move over the top of colder air at the surface. That's a process where we got warmer air moving in, warm air advection. On the backside of the low pressure system on northwesterly winds, we now have CAA, which stands for cold air advection. So colder, drier air is moving in behind your cold front and behind that deep low pressure system over northern Missouri. So we get a lot of strong temperature drops, fairly significant temperature drops over Kansas and eastern Oklahoma. The image on the right shows a baroclinic high, and see how the pattern is somewhat reversed. We get warm air advection out ahead of lows, but we get cold air advection out ahead of baroclinic highs in the northern hemisphere. So we have a lot of cold air advection. You have a high pressure system situated over upstate New York, and there's a strong north and northwesterly wind blowing over the waters of the western Atlantic. And that's bringing a lot of cold air advection from Canada into the mid-Atlantic region, the western Atlantic Ocean. On the backside of high pressure systems, we get more of a southerly or southwesterly wind. And in this case, you see two distinct areas of WAA, or warm air advection. So generally, your temperature pattern is going to be determined by where are you located in relation to the high and low pressure systems that go across the United States in the fall and the wintertime and early spring. Are you located to the east of cold Canadian high pressure systems? In that case, you're most likely experiencing colder northerly winds, very cold temperatures. If you're on to the west, on the backside of high pressure systems in the United States, you're most likely getting warming temperatures, warm air advection over your area. Okay? So it really determines where you're at in relation to these two pressure systems, the low and high pressures. Right. So with weak thermal advection, we mentioned this. Weak thermal advection exists in the center of the low and high pressure systems. It cannot significantly change the central pressure because it's so weak, except when you have systems that are just starting to develop. Then that weak thermal advection, that could be the mechanism that really gets things going as far as deepening and filling of lows, building or weakening of highs. So it's critically important to upper level systems. When we have any kind of thermal advection, it also influences the steering of baroclinic systems. So wherever your strongest warm air advection occurs, the surface low pressure track is going to move toward the region of the strongest warm air advection, or it's going to be taking that path of least resistance where the strongest amount of warm air is moving into an area, that strong warm air advection. It's going to be the low pressure system is looking for the path of least resistance. And in general, that coincides with your areas where the pressure falls off the greatest. Surface highs are going to move, on the other hand, towards regions of strong cold air advection. So wherever your strongest cold air advection is occurring, that's where your surface highs are ultimately moving towards. So here's the steering mechanisms. I'm just showing you graphically on another 1,000 to 500 millibar thickness chart here. Thickness charts are great charts to use when analyzing cold and warm air advection. Generally, we're showing you there's a low pressure system over lower Michigan, and I have a black arrow pointed towards that WAA, the warm air advection area. That low pressure system is following or moving towards that area of strongest warm air advection. And then the high pressure system over western Kansas, I got a black arrow also heading pointing towards the strongest area of cold air advection, abbreviated by the initials CAA. So that high pressure system is pretty much scooting to the east-southeast. All right, now in addition to temperature or thermal advection, when we talk about mid-latitude systems on the synoptic scale, we also have to talk about vorticity advection. Now, I have mentioned vorticity advection on, I've explained it a little bit on my weather charts, my weather videos during the winter months, especially because these lobes of vorticity are stronger in the wintertime than they are in the summer. So they play a significant role in upward vertical motion or downward vertical motion in the atmosphere. So we're going to cover the vorticity advection aspect as well. And when we talk about vorticity advection, vorticity is simply just the spin of an air parcel. Think about vorticity as the spin of an air parcel. So we have, with vorticity advection, when we see divergence aloft, and I mentioned this in previous videos, divergence is referring to the removal of mass aloft, or the spreading apart of height contours, or perhaps you have air parcels that are moving much quicker further downstream than where you're located. Right? So divergence aloft is removal of mass, and this is indicated by what's known as positive vorticity advection aloft. So you have a lobe of positive vorticity advection, and you have this divergence aloft. As a result of that removal of mass aloft and that divergence aloft, you get low-level air which meets and rises and converges and rises in the atmosphere. And this increase in cyclonic vorticity will then occur at the surface as a result, and that's going to deepen your surface low-pressure systems, and it will weaken surface highs. Because high-pressure systems want convergence aloft, low-pressure systems want divergence aloft. So low-pressure systems want that removal of mass aloft. As you remove mass aloft, it must be replaced from below, and therefore you get increased low-level convergence where air streams are converging or meeting, and that air rises. With high-pressure system, it's the opposite. Whenever you have convergence aloft, or the air meeting and mass accumulation higher up in the atmosphere, that air eventually is going to sink. And convergence aloft, or the addition or gain of mass aloft, is going to be indicated by what's known as NVA, or negative vorticity advection aloft. And that, as the air sinks in the atmosphere, you have the upper level convergence, airstreams meeting, the mass accumulates, the air sinking vertically, and as soon as it hits the surface, it's going to spread out horizontally along the surface, and that's known as low-level divergence. So convergence aloft leads a low-level divergence at the surface, sinking air motion. This is going to increase the anticyclonic vorticity at the surface, and low-pressure systems definitely, that's not favorable for them to develop convergence aloft, because you're adding more mass aloft, which is going to basically fill the whole air column with mass, and that's going to fill your surface lows. Convergence aloft, however, is going to build your surface highs. So surface highs like that addition of mass aloft is giving them more, it basically results in increased downward vertical motion. Let's take a look at the stack of these baroclinic features, these baroclinic systems. We talk about that positive vorticity advection. We talk about vorticity advection and its interaction with an area of low pressure at the surface. So you have this area of low pressure at the surface marked by the black L. You have the warm front and the cold front extending out from the low pressure center. You have these height contours, which are your solid black lines. They're 500 millibar height contours. So we have an upper level trough. Two things of note here on this, okay, that are going to impact the development of this low pressure system. The purple shading represents the PVA, or positive vorticity advection. I am getting higher vorticity values to move over the top of this low pressure system. It's all in the purple shading. Okay, that generally occurs out ahead of that shortwave trough axis, the purple shading. Okay, showing you, first of all, there's positive vorticity advection aloft, and I want you to pay attention to the black solid lines just to the basically to the upper right of the low pressure system. Those height contours, those black solid lines, are slightly spreading apart. This is a process that's known as divergence. So we're moving mass aloft, and we have an area positive vorticity advection, which is going to result in rising air motion, and that's going to result in ultimately a deepening of this low pressure system. And where can you find the vorticity advection? You would simply look at a 500 millibar vorticity chart to kind of see where those vorticity lobes are, whether you have positive vorticity advection or negative vorticity advection. All right, so baroclinic lows, just bottom line, they're going to tilt with height. And they're linked to these major shortwave troughs. This is an example of a major shortwave trough and positive vorticity advection, PVA. They're linked to those major shortwave troughs. Those major shortwave troughs typically occur on more than one vertical level. So the main area of the atmosphere where we're going to see these vorticities and these troughs, these shortwave troughs and ridges, is going to be basically up at around 18,000 feet at 500 millibars. But with a major shortwave trough, that trough extends through a greater vertical depth of the atmosphere in more than one layer. And generally, baroclinic lows are going to be found within areas of divergence ahead of the trough, and that's what I was showing you here, how the height contours, the solid black line spread further apart. And then divergence aloft is going to deepen the surface low. It's going to get stronger. Now with a baroclinic high, now you notice the shape of the black solid lines, the height contours has changed a little bit. So now we have a case, we have a shortwave ridge in this case. The solid black lines are indicating a shortwave ridge. The shortwave ridge axis is indicated by that sawtooth looking line to the west, to the left of that high pressure system at the surface. The purple shading indicates negative vorticity advection, or NVA for short. And we also have the height contours to basically to the bottom right, away from that surface high, are coming closer together. So that indicates upper level convergence due to the direction of the height contours getting closer together. And we have negative vorticity advection. So upper level convergence and negative vorticity advection are going to result in a building high pressure system. The high is going to get stronger. So with baroclinic highs, they also tilt with height, and they're linked to these major shortwave ridges. The shortwave ridge axis, again, is indicated by that jagged sawtooth line. And they're found generally within areas of convergence ahead of the ridge, associated with that negative vorticity advection, NVA. And the convergence aloft, you're adding mass aloft, the greater the amount of mass aloft that is put together, the greater the sinking air motion, and the stronger your central pressure is going to be at the surface. So that is how baroclinic systems stack. They are associated with features, shortwave troughs and shortwave ridges aloft that do support them. So again, when we're living here at the Earth's surface and we have rain or snow, maybe you have a lot of wind, maybe you have a pretty good, for example, storm in the wintertime, you have to look three-dimensionally all the way through a fairly deep layer of the atmosphere. It's all connected. The surface lows, the surface highs are linked up with the mid-level shortwave troughs and ridges and positive and negative vorticity advections, and then even to the jet stream if you have a jet max up at 30,000 feet, 300 millibars. So you have to look in a three-dimensional aspect of the atmosphere. It's all connected. All right, now we're going to move on to adiabatic processes. Now, adiabatic processes, simply put, that refers to a process in the atmosphere where there's no exchange of heat with the surrounding area, with the surrounding atmosphere. We have these air parcels, these imaginary air parcels, vertical motion processes when we talk about adiabatic processes. Bottom line is, as air rises, it cools and condenses. It wants to expand. That parcel wants to expand due to lessening pressure. And as a result, you get adiabatic lifting, ascent of air. That's going to promote that net cooling effect. Sometimes you get a net warming effect if you have the air sinking, right? If the air's rising, it's going to be a net cooling effect because as air parcel rises, it expands and cools. As the air sinks, if you were to sink an air parcel, it's going to basically get more compact and contract, and it's going to get warmer, and it's all going to be dependent on the stability of the air mass, of the warmer air mass. So generally you have ascent. Ascent is a fancy way to say rising air motion is found ahead of low pressure systems, and you have ascent is also found, the rising air motion is also found behind high pressure systems in the northern hemisphere. This affects the development of baroclinic lows only, the ascent aspect. Generally, the air being lifted on the synoptic scale is stable. Stable air must be forced to move vertically, but how much forcing is required to lift the air depends on the amount of stability and moisture in the air. So if you have a very moist and unstable atmosphere, it's going to take much less energy to cause the air to rise. If you have a more stable, dry atmosphere, energy is going to be utilized in trying to force the air to rise, which is going to take energy away from the developing system. So here it is in red, just a quick breakdown, the red font. Energy must be taken from a developing system and used to lift stable air. So you're taking the majority of the energy and it's trying to lift that stable air, and therefore you're not going to have much energy left over to really develop the system. That's going to act as a braking mechanism, slowing the development of the system. So with stable dry air, when I talk about dry, I'm talking about unsaturated air. Air that's not reached 100% relative humidity. It's not reached its saturation point. So stable dry air with lifted condensation levels at high altitudes greatly slows development of baroclinic lows. Now, lifted condensation levels are simply the point at which the temperature and dew point are the same, where saturation occurs, and it's a point at which you see the base of clouds. If you look up at clouds during the day, you'll see their bottom undersides, the base. If that base is higher off the Earth's surface, that means we have very stable and dry air mass in place, and therefore you're going to have a much slower development of baroclinic lows. Upon lifting that stable dry air, it becomes much colder than the surrounding environmental air, and it wants to sink, okay? Because it's cold and dry, that's going to result in thickness values that are much lower. And it's a significant drain. Stable dry air is a significant drain on cyclogenesis process, with significant development not likely, or a cyclone may not form at all. So you may have here's an example in the wintertime. You have this strong, cold, high pressure system that moves into your area. Cold, dry air mass is in place. You get an area of low pressure that tries to form, baroclinic low tries to form to the southwest. It's moving towards the area where you're located, but you still have a cold, dry air mass. You're still stable air mass in place. That air you're just not going to get the energy involved is going to be utilized in trying to lift that stable, dry air, and it's just not going to be an effective process for cyclone development, for cyclogenesis. Now, on the other hand, if you have stable, moist air, so now we have saturated air where the relative humidity is 100%. This is going to slow development, but not as greatly because the air is moist. So stable and dry is the worst case scenario to try to develop a low pressure system, because the lifting is, number one, the cloud bases are so high up in altitude. And then with moist air, stable moist air, with being stable, that's still not an ultimately favorable scenario for cyclogenesis, for low pressures to develop or intensify, to deepen, but it still will develop. So upon lifting, you get the stable moist air. It's not going to cool as fast as stable dry air. Thus, there's less energy expended in forcing the air to rise. So the atmosphere is not using as much energy to force this air to rise because you do have a moist aspect to it. Moist air tends to be less dense and wants to rise. The atmosphere expends some energy, but the fact that the condensation readily occurs upon lifting allows latent heat of condensation to partially offset cooling. So one thing I want to mention in the atmosphere, as the air rises vertically, eventually the temperature reaches the dew point, 100% saturate, 100% relative humidity and saturation occurs. Clouds form, condensation occurs. In the process of condensation, where you're going from a water vapor to an actual liquid, the cloud droplets, that's going to release what's known as latent heat to the surrounding atmosphere. And that latent heat is going to offset the cooling of the air as it rises. So more energy is going to be available to aid the development of a low pressure system, cyclogenesis, than with dry air. So the net effect with stable moist air is some energy is removed from the cyclogenesis process, but partially returned when you add that latent heat through the process of condensation. And it is less of a drain on a system development, and more energy is available for development. Now, this initially unstable air is what you really, really want to get low pressure systems develop and to intensify, to deepen rather rapidly. The conditionally unstable air affects systems differently depending on whether it's forced to rise or sink. Conditionally unstable air is associated with a low. It's forced to rise. The air is forced to rise. Conditional instability means that upon lifting, saturated parcels may eventually become unstable. So if the parcels are saturated, they can become unstable. If they're unsaturated, it's going to take some more work by the atmosphere. So in general, air must be lifted to what's known as a level of free convection. The level of free convection is a point on an upper air sounding. Once a air parcel reaches a level of free convection, anything above it is going to be much more unstable. Right? The parcel ultimately becomes warmer than the environment and contributes to a local increase in the thickness. When you have a warmer atmosphere, you're increasing or expanding the atmosphere, it's getting taller. That local increase in thickness means that more energy is added than is taken, and this favors further development. Okay? And then stable or conditionally unstable air associated with a high. When you have a high pressure system, if the air is sinking, that's exactly what a high pressure system wants. You get, as air sinks, you have this warming effect due to air subsiding, dry adiabatically. This is going to cause a local increase as the sinking air becomes warmer. This increase in thickness due to adiabatic warming of the sinking air retards anticyclogenesis. So for anticyclogenesis, or the strengthening or building of a high pressure system, you want colder or lower thicknesses. In this case, we're warming the air due to sinking air motion, and we're increasing the temperature. In addition to adiabatic effects, we need to talk about what's known as diabatic effects. All right, so for diabatic effects, this process involves the transfer of heat or energy between the air parcel and the underlying surface. Kind of going back to air masses, my training video on air masses. As the air mass moves out of its source region, it's going to undergo modifications, changes in its temperature and moisture content. Because as the air mass moves over a colder or warmer ground, it's going to undergo some changes or modifications. Same thing goes here with diabatic effects. Transfer of heat energy between air parcel and the underlying surface. The differential heating, or the difference in heating or cooling of air at a given location with respect to surrounding regions, causes development. So if we have air that's over a warmer surface, it's going to be heated from below, and that's generally going to favor rising air motion in the atmosphere, and that's going to result in cyclone development. A forcing mechanism for heat low is associated with continental tropical air masses, for example. So even in the summertime, when we have these CT air masses, continental tropical air masses, the extreme heating of the desert by the sun, that's a forcing mechanism that forms that heat low. It's a secondary effect for baroclinic lows, and a low moving over the Great Lakes in winter will slow down and deepen due to the diabatic process. So think about a low pressure system over a body of water in general, especially like the Great Lakes in the wintertime. The Great Lakes, that water is generally going to be warmer. So as that low pressure system moves over a warmer surface, you have colder air aloft above the surface low pressure system. As that cold air moves over that warmer water for the Great Lakes, it's going to result in instability, and it's going to result in that low slowing down once it gets over the Great Lakes and getting stronger or deepening because of the unstable character with the cold over the warm in that situation. Now, air over a colder surface is going to be cooled from below, causing high pressure development or anticyclonic development. Forcing mechanism for cold equivalent barotropic highs associated with continental polar air masses. It's a secondary effect for baroclinic highs. A low moving over the Great Lakes in summer will speed up and fill due to the diabatic process. So that same low pressure system that slowed down and deepened in the winter, cold over warm, has now become a situation where the lakes in the summertime are cooler. And as a result, you're going to have generally a cooler, lower level of the atmosphere, which is going to stabilize that low pressure system and actually cause it to fill and to speed up. So this is a summary of the cyclogenesis and anticyclogenesis influences. For cyclogenesis, remember the definition of that is the development of a low pressure system or the intensification of an existing one. We have positive vorticity advection at 500 millibars, so the vorticity values are increasing over that surface low. That's going to be indicative of divergence or removal of mass aloft, and low-level convergence, air coming together and rising from the surface up in the vertical. Locally concentrated warm air advection occurs in the lower troposphere. We have weak static stability of lifted air and abundant moisture. When you have abundant moisture in the atmosphere, those LCL, lifted condensation levels, those elevations or heights of the cloud bases are going to be much closer to the surface. For anticyclogenesis contributors, that's your high pressure systems, we now have negative vorticity advection, NVA, at 500 millibars or 18,000 feet. That's going to be indicative of convergence or the gaining of mass, the addition of mass aloft. And then as the air sinks in the atmosphere, eventually sinks, hits the Earth's surface, and spreads out, low-level divergence. Locally concentrated cold advection in the lower troposphere, anticyclones or high-pressure systems, baroclinic highs, they really like cold air advection in the lower troposphere. And then weak static stability of sinking air motion. As air sinks, it is going to warm and the atmosphere is going to compress. And then finally, on part one of the video, I'm going to wrap things up with a little discussion on what's known as baroclinic instability. And this research was done by Holton in 1992. Baroclinic instability basically is the process by which short waves amplify or they increase their amplitude over time by extracting or taking energy from a north-south temperature gradient. That's what the baroclinic instability definition is. And let's break it down a little bit. So for example, the image on the left, I'm showing you 540 decameter height contour, and then I'm showing the 546 decameter height contour below that. The red sawtooth line indicates the shortwave ridge axis. The blue dashed line indicates the shortwave trough axis. So you notice I want you to pay attention to the amplitude of these height contours over time. The image on the left is showing the height contours. There's a little bit of amplification to it, a little bit of a dip in the height contours, a little bit of a building up where that sawtooth red line is, that sawtooth ridge line is. But look at the image on the right over time. What happens? Your shortwave trough gets deeper, your height contours dip down with much greater amplitude, while the sawtooth red line, the image on the right, shows that shortwave ridge building or getting taller in the atmosphere. So you see a amplification of the shortwave is what I'm showing you in this particular example. Now, baroclinic instability is the primary mechanism responsible for development of mid-latitude synoptic scale systems. Whether we're talking about baroclinic lows or baroclinic highs, this baroclinic instability is so very important. And it helps to maintain the global heat balance by transporting warm air northward and the colder air southward. It's all about a balancing act of the atmosphere. I say this a lot in my videos, but it's so very true. What is the consequences of this baroclinic instability theory? The first consequence is long waves are relatively stable. When I'm talking about a long wave, I'm talking about a wave located at the jet stream level. Your troughs and ridges up at 300 millibars or 30,000 feet. In general, the longer waves are relatively stable, while the major short waves are embedded within that long wave pattern. Those major short waves are most likely to amplify, and they're much more unstable as compared to the long waves. So development of systems through the process of baroclinic instability, tropical warming and polar cooling. All right, that is going to really set things in motion here when we talk about baroclinic instability. We're looking to try to develop and increase a thermal gradient or temperature gradient. When we have tropical warming and the polar areas cooling, we are increasing our north-south temperature gradient. The baroclinic systems are then going to use that temperature gradient as a source of energy, potential energy being energy due to position. That potential energy eventually is going to be converted to the energy of motion that's known as kinetic energy. So that temperature gradient is essential to really get things going. Here's an example of thermal and contour troughs in a major shortwave. And whenever we're talking about baroclinic waves or baroclinic systems, we're talking about an out-of-phase relationship. So in this case, the dashed dark lines represent your lines of equal temperature, or isotherms. And notice that our isotherms are labeled -10, -15, and -20 degrees Celsius. And then we have the solid black lines which indicate your geopotential height, or height contours in the atmosphere. And they're represented by the values 540, 546, and 552. So you notice how my dark solid height contours do not perfectly mirror my dashed isotherm lines in this example. Do you notice how the black solid lines cross those dashed lines, those lines of equal temperature? That is an example of an out-of-phase relationship. These two height contours and isotherms, these two features, are not perfectly aligned over the top of each other. In this case, when we're out of phase, we're going to get colder air advected into the shortwave trough, and then the warm air is going to be advected into the shortwave ridge. And so cold air advection ultimately is going to deepen the trough, and then warm air advection is going to build the ridge. And then we're going to have amplification of that wave, the short wave, over time due to this out-of-phase relationship. Colder air pouring into the trough, warm air moving into the ridge, and you're going to get a greater amplitude to the wave over time. So this potential and kinetic energy is going to be transferred to the major shortwave via that temperature or thermal advection. And the thermal advection is going to cause upper level ridges to build and troughs to deepen. And I just mentioned that cold air advection is cold air moving into the trough, warm air is moving into the ridge, and that's going to create an amplification of the wave, and that's called mainly due to the fact we have baroclinic instability. So large energy transfers must occur for a major shortwave to develop. You must have intense advection or changes in temperature throughout the troposphere, and there must be a well-developed baroclinic low and baroclinic high to enhance the advection in the lower troposphere. And the way these baroclinic lows and highs enhance the advection in the lower troposphere is due to a stronger pressure gradient, tightening pressure gradient, stronger northerly winds, stronger southerly winds. Here is, in general, a great image graphic showing vertical motions associated with mid-latitude systems. We have an L for low pressure, we have H for high pressure in this image, showing you ascent equaling rising air motion. That's where you're going to get your clouds and precipitation, where you see the orange ascent areas where the air is rising. And you get descent, that purple shading indicates where air is sinking, where you're generally going to have much nicer weather. So this kind of shows you, depending on where you are in relation to this storm and the frontal boundaries associated with the storm, that's really going to determine if you're in the ascent area, rising air, or descent, sinking air motion. And that's really going to determine what type of weather you're going to get. So with baroclinic instability, you get this temperature gradient, you start to get amplification where your height gradient is going to represent the potential energy source, which then is converted to the energy of motion, kinetic energy in the shortwave. That potential energy is converted to kinetic energy in order to develops that low-level circulation, or that spinning motion. We start to get the air masses starting to mix with each other, cold moving towards warm, warm moving towards cold. You get that circulation around those baroclinic low, that potential energy from the tightening pressure gradient, or the tighter isobar packing, is converted to kinetic energy as air accelerates across the height gradient from high to low heights. And in that energy conversion in the process of baroclinic instability, that energy conversion process results from the instability, and as you have cyclogenesis and anticyclogenesis proceeding, that thermal or temperature advection or movement, the temperature changes increase, and you have more potential energy converted to kinetic energy. The increasing energy of motion or kinetic energy then strengthens the low-level circulation, and the process will repeat, and the system ultimately deepens and grows over time till it reaches a breaking point. All right, that wraps things up today on the training. We ended it with baroclinic instability. Very interesting topic. We talked about mid-latitude systems. This is part one of the training. This is where to find us on social media. Again, Spot on Weather, we're at Facebook, Instagram, Twitter. There's our website, Spot on Weather Weebly. Just Google Spot on Weather Weebly and you'll find us. I guarantee it. Check us out. Subscribe to Spot on Weather here on the YouTube channel for the most accurate weather forecast, as well as we do this training. Hope you got a lot out of the training today. I try to break things down in simplistic terms. Weather can be really, really technical, the science behind it. So I'm trying to break it down and make it as easy and simplistic as possible for you to enjoy at home. I really hope you enjoyed this. We still have a couple more parts on this particular topic, mid-latitude systems. So very appropriate right now as we head into a more dynamic period of weather here in the fall into the winter. That wraps things up. I hope you enjoyed it. Spot on Weather. If we're not spot on, we're not doing it right. Take care, everybody. Have a great, great day.